Hello, everybody. First off, thank you to the Explorers Club. Thank you for the local team here. Thank you to Richard, Brooke, Nina, for inviting me here today. This is my first time at the Explorers Club. This is my first time at Tercera. I'm having an amazing time getting to know a lot of you. I hope to get to know all of you, or at least as many as I can in the next few days. But like Richard said, I'm going to change tone here for a second. We're going to go to a different part of the solar system. And I'm going to tell you a story. And we've heard the power of stories and why they're useful and how they're an effective way of communicating science or why we want to do something. And I'm going to talk about soaring through the skies of Venus. And first I'm going to tell you why, and then I'm going to tell you how. So it starts with Venus, a world that really we don't know that much about. But it is important for me to kind of emphasize, if nothing else to you, that it is the only other Earth-sized world we will ever visit. Certainly in the foreseeable 10 or 20 millennia, we are not going to go to extrasolar planets, those orbiting other stars. So if we want to understand the secrets to long-term habitability, we heard in the previous talks that Earth has been habitable for billions of years. We know, and we'll hear in Nina's talk, that Mars, for example, has not been habitable for nearly as long. And so one of our big questions we have is, how do you get a large world and how do you keep it habitable? Now, how life comes to be and what that means, that's a different question, and we don't have the answers to it yet. But we are beginning to ask, how do you sustain habitability? And the way you answer that question is you understand what happened to Venus. Let me tell you why. So first off, let's talk about some basics. It's 95% the size of Earth. So functionally, it's Earth-sized. And this is important because you might have heard in the news, let's say, that, oh, astronomers have discovered an Earth-like world somewhere else in the universe. Well, we haven't. We have detected Earth-sized worlds. But the difference between Venus and Earth is such that our error measurements can't distinguish one from the other, which means that when we discover a large rocky world orbiting another star, it could easily be a Venus as it is an Earth. And so we don't have the ability to distinguish between those two yet. So it's Earth-sized. It's not quite the mass of Earth. It's 82% the mass of Earth. It's a little less dense. And it orbits about 3/4 the distance from the sun that Earth does. So it receives about twice as much sunlight. But on paper, it's a pretty similar looking planet to us, at least from far away. And I want to just point out here, this is a composite image from the Japanese Akatsuki mission. This is what Venus looks like on the night side in the infrared. And that glowing color is the lower atmosphere glowing up through the clouds. This is what Venus looks like in the daytime in the ultraviolet. To our eyes, it's essentially a featureless billiard ball. But it has an amazing atmospheric structure, which I'll show you. Now, the first successful planetary flyby of any spacecraft a human sent out ever wasn't to Mars, it was to Venus. It was NASA's Mariner 2 mission in 1962. And one of the important discoveries that Mariner 2 made, or in fact didn't make, was any sign of habitability. In fact, Mariner 2 confirmed that the surface conditions on Venus are, well, essentially hellish. Now, this is a computer-generated image of what the surface of Venus might actually look like. But we do know from very limited chemical data from the surface that the pressure at the surface is 90 times what it is in this room right now. It's equivalent to 900 meters under the ocean. That's the standard pressure of things at the surface. It's 470 Celsius at the surface, average temperature. In fact, it's the same temperature on the day side and the night side, and it's the same temperature at the equator as the pole. Now, often when people describe Venus, they'll say, oh, that's hot enough to melt lead. I have no intuition for what it takes to melt lead, but I can tell you that this is the temperature of a self-cleaning oven. So if you want to clean your oven, this is what it's doing. It's Venus. It's just 1/90th the pressure of Venus, but it's the same temperature. So this is pretty bad. But we have had a few spacecraft land, about 6 of them, and we do know that the rocks are made of basalt. And to our American friends, that's basalt. It's a common stuff. It's what we're standing on right now. It's what most of the ocean floor is made of. And this is the kind of rock that Mercury is made of, and that much of the moon is made of, and Mars is made of. So we know this is a standard kind of thing you get in the solar system, and probably elsewhere in the universe. So we know a little bit about it. And some of that information comes from some of the Venera landers of the Soviet Union successfully touched down in the 70s and 80s. Now these things, they're about this big, titanium ball that basically drops onto the surface. Ask me later how we actually get onto the Venus surface, because it's wild. These things sat there for about 2 hours before the temperature baked their electronics. So we don't know much about the surface. We have 6 images in total of the surface of Venus. But we know enough to sort of get a rough sense of what's going on. Now, the skies of Venus, which is the focus of this talk, they're an interesting place. We know that they're about 97% CO2. which interestingly is the exact same composition as the atmosphere of Mars. Mars and Venus have the exact same atmospheric composition. There's just a lot more air on Venus, and so it has weather. We know that there is a global layer of clouds. These clouds, unlike those of Earth, which are made of water vapor particles, they're made of sulfuric acid. Sulfuric acid is problematic for a whole pile of reasons, but it is also bright, and it reflects a lot of light. And so we all know Venus is the morning star or the evening star, depending on when you see it in the night sky, or the evening sky or the morning sky. And the reason it's so bright is because of that global layer of sulfuric acid clouds. Another name for Venus is Lucifer, probably an appropriate term for the planet. But even then, there's something interesting about the sky of Venus. It is the only other place in the solar system that is the same temperature and pressure as this room. At about 55 kilometers altitude, slightly above the clouds of sulfuric acid, it's essentially room temperature and pressure. So an astronaut, conceivably, as long as she or he were shielded, wearing some sort of plastic suit to protect them from sulfuric acid droplets, and had a breather, a mask on, they could comfortably go out in shirt sleeves onto, say, the gondola of an airship and be perfectly safe. It's the only other place in the solar system at room temperature and pressure, and the Soviets took advantage of this. In 1985, they flew 2 balloons, Vega 1 and Vega 2. Now, the Vega missions were wild. It turns out they were actually going to go to Halley's Comet. And some Soviet engineer pointed out, well, we need to fly past Venus to get to Halley's Comet. While we're going to Venus, let's just drop in a lander and a balloon. And they did. And the Vega 1 and 2 balloons flew for about 44 hours each. Now, they were small. As balloons go, they're about that wide. They had maybe 12-kilo payload. Very, very basic, simple stuff, but they demonstrated that you can fly a balloon on Venus. And in fact, it is one of the least inhospitable places in the solar system. Now, we've learned a great deal about Venus since. There's still some fundamental questions we don't have answers to. We have some idea of what we're talking about now. We do know, for example, thanks to Venus Express, which was a European mission which operated from around 2005 to 2014, Venus Express detected some interesting stuff on the surface. Now, you'll hear about Mars and a world that has a different kind of geology to our own now, but you saw that Earth, you know, Earth is a vibrant, living world. What we don't know is how vibrant or living Venus is, but we've had some tantalizing hints. We do know, for example, that the amount of sulfur dioxide, which is a volcanic gas, seems to go up and down every so often. We don't know why, but we do know that the amount is not stable, it changes. We do know that, for example, there are places where the ground seems relatively hotter, and then it cools down. And this cooling might take a few weeks. We've seen that a few times. And it was because of the Venus spacecraft, the Venus Express spacecraft in the 2000s, that was able to detect these so-called transient hotspots, that it's led to this tantalizing suggestion that there's active volcanism taking place on the surface of Venus today. Now, if that's the case, that has profound implications for all kinds of things, because volcanoes are an effective way of not just helping a world cool down, but also replenishing an atmosphere, because our oceans and our atmospheres come originally from volcanoes. And in the case of, say, Mars or Mercury or the Moon, if you don't keep replenishing that stuff out of volcanoes, the solar wind will strip it away. But in the case of Venus, it's held on to a much greater atmosphere than Earth has, probably because of volcanics. And there was something else that was fascinating about a mission called Pioneer Venus, which NASA flew in the 1970s. In fact, Pioneer Venus flew from 78 to 1990, it orbited. And it had a set of probes that it deployed when it first got to Venus in 1978. And these probes detected something interesting in the atmosphere. What they found was that there's evidence for a sustained history of water loss. Now, I'm going to skip the details. It has to do with looking at 2 different isotopes of water. But the point is that these probes found evidence that Venus has lost at least an Earth ocean's worth of water over the past 4.5 billion years. Now, what that doesn't tell us is whether that water was in the form of steam in this hellish world that was always too hot, or if in fact, and this is the tantalizing possibility, Venus may once have had liquid water oceans. Now, these 2 scenarios are some of the 2 most important questions we have to try and answer in planetary science. And the reason they're important is because they speak to a fundamental question that I mentioned earlier. How do you get an Earth? And how do you keep an Earth? So one possibility is that Venus always was hot. It was simply closer to the sun. It was never able to cool down. And as a result, although it had a lot of water, it was steam in this horrid steam-rich atmosphere. And essentially, the Venus we see today is the Venus that's always been there. And if that's the case, then when we look at telescopes at other planetary systems and we find Earth-sized worlds, well, the ones closer to their star are probably like Venus. Okay. The other possibility is that Venus may have had liquid water. It may have cooled down enough to condense that steam from its atmosphere, just like Earth did, very, very early on. For that water to condense into ponds, rivers, streams, lakes, seas, oceans. And if that's the case, we have climate data, at least, that suggests that such a transition from a world like this to a world like Venus today could have happened as recently as 1 billion years ago. Now, normal people don't think billion years is recent, but planetary scientists are not normal people. We're used to thinking about very great spans of time. And 1,000 million years ago isn't that long as planets go. It's about maybe the last fifth of the planet's life. And so if it's possible that for a while there were two large blue marbles in the solar system, that's one of the most important questions we can possibly try to answer right now, because the answer either way has profound implications for our understanding of how Earth has stayed habitable for so long. And that's where soaring through the skies come in. So I mentioned that the atmosphere of Venus is a place where you can operate for a while and it's relatively benign. And in fact, there are gases in the atmosphere that, if we measure them, we may actually get an advance on our understanding of how Venus has come to be. And that's exactly what NASA's planning to do with the Da Vinci probe in 2029. The plan is this Da Vinci probe, about 1 meter across, a titanium ball essentially, will be dropped through the sky, and on the way down, it will take a whole bunch of measurements, including noble gases, which we think are important for understanding what the history of Venus has been like. This descent will take about 60 minutes, and it will do, on the way down, it will take high-resolution images of the surface. Now, Da Vinci is going to be the first time NASA has gone back to Venus since 1994. And it's the first time that NASA sent a probe into Venus since 1978. And with modern technology, we are going to learn an amazing amount of stuff from this. This is what's exciting about Da Vinci. It's going to tell us some really important things. But it's only going to spend 60 minutes in the sky. And it's not going to take measurements in the clouds themselves, which is where some of the most important measurements remain. And so, although this is going to be exciting, and it's going to be the next step in our understanding of Venus science, it's not enough. It's not going to answer all the questions we have. But we can turn to balloons, just like the Soviet Union did in 1985. And in the last 10 years, NASA's put a lot of work and time into developing technologies to allow us to fly balloons on the surface of Venus. And it turns out that because you don't have those high temperatures and high pressures, because it's room temperature and pressure, you can fly a balloon for weeks or even months at Venus. In fact, what we try and tell people is that balloons are to Venus as rovers are to Mars. We know that some of the rovers on Mars have lasted more than a decade because the conditions there are relatively benign. Well, so too could we do with a large balloon. We would fly this for months. It would be carried, just like balloons on Earth, by high altitude winds. And then at the bottom of this thing, you'd put a set of instruments in a gondola, suspended by a tether from the balloon. Now, I've been giving this talk for about 8 months. I'll talk about a project I've been involved in for the last year and a half. A couple of months ago, you may know that the, high-altitude balloons were in the news a little bit when China seemed to float one over the United States, and then the US shot one down with a fighter jet. So we've had to become very careful in where we do our flight testing to make sure the US Air Force doesn't shoot our stuff down. But the point is, high-altitude balloons have been used for years on Earth, for meteorology, for science, for all kinds of tech demos. And we know they work on Venus because that's what the Soviets did in '85. And that's what's underpinning work that we're working on, myself and others across the United States and Europe as well, with the JPL, the Jet Propulsion Laboratory, to develop a concept for a long-duration balloon. In fact, one of the things we're looking at is what we call a variable altitude balloon, a technology that would allow us to change the altitude of the balloon. There's a balloon inside a balloon, and by exchanging gas between the two of them, it looks kind of peanut-shaped. We're able to change the altitude of the balloon, and in doing so, we can catch different winds at different altitudes and be blown passively by those winds in different directions. And that allows us to explore different parts of the atmosphere of Venus. Once we have one of these things in the Venus atmosphere, one of the things we can try and do is listen for infrasound. Now, you'll hear a bit more about this in Nina's talk in a bit. One of the benefits of infrasound is that it's an effective way of listening for the heartbeat of a world. And on Earth, we know that we can fly balloons, and we have barometers on those balloons, and they can detect the energy coming from, say, an earthquake or a volcanic eruption, and that energy travels through the air. Now, I told you that the atmosphere of Venus is extremely high pressure, and as a result of that, that coupling from the ground, say from a quake, to the air is 60 times stronger. So we can fly a balloon at 55 kilometers with very sensitive microphones, and we will listen for the heartbeat of this planet. We will listen for things exploding in the atmosphere. We will listen for quakes. We will listen for volcanic eruptions, for landslides. We will listen for wind. That's what you can do with this balloon that operates for a long time. And one of the really exciting things you can do is you can search with a magnetometer for evidence of rocks on the surface of Venus that were once magnetized. One of our big questions is, why does Venus not have a magnetic field? Earth has a magnetic field today, and we know it's had one for several 100 million years at least. We know that Mercury had one a very long time ago. Mars had one a very long time ago. Mercury's is still there, or at least a new one came back. We don't understand much about magnetic fields. We don't really understand how they help retain an atmosphere, or even if they're needed for it. But we do know that one of our big questions is, why does it not have a magnetic field? Now, we can search for ancient evidence of rocks that had a magnetic field when they were emplaced by putting a magnetometer, which is a thing we've put on airplanes the whole time on Earth. We fly it from a balloon. Now, in the future, this has not stopped people conjecturing about what might happen later in this century, perhaps. People have proposed that you could do long-term human habitation. There's this concept called havoc, which is really just a really nice idea and sexy renderings. But the idea is, maybe later 2070s is probably optimistic, probably 2100. But in the future, maybe we will see humans operating in large cloud-based stations with big rockets that allow them to go back into space. Maybe. But what we're trying to do right now with a concept we call Phantom is to soar through the clouds of Venus with technology we're developing today. And so I like to show people, this is an artist's impression of one of the balloons that we've been developing with a company called Near Space Corporation. This is funded by NASA and the Jet Propulsion Laboratory. And this is an artist's impression. This is a photo of the New Zealand sky. I took out an airplane window, and I made it yellow, and I stuck this little balloon. By the way, we think above the clouds, the sky is probably blue, because the refraction, the scattering of sunlight, the gases are similar to what they are on Earth. Even though they're different, they have the similar scattering properties. So above the clouds, it's probably blue sky, just like it is on Earth. And so maybe this is what it would look like if you actually had a balloon flying through the skies of Venus. But this is actually a real photograph taken from this scene, because last summer, for the first time, we flew a variable altitude balloon in the Black Rock Desert, Nevada, to test bed the technologies we will need to do to fly a full-size balloon through the skies of Venus. And I'm going to finish with a short video that documents some of the test flight data we got last year. So take a look. So stay tuned, folks, because our plan is to fly this thing late next decade of Venus. And when I do, I'll be happy to come back and tell you how it went. Thank you very much.